Hi, everyone. It is my pleasure to attend this webinar and to give a presentation on our research on municipal solid waste incineration bottom edge for civil engineering materials. My name is En Hua. I'm an associate professor at the School of Civil and Environmental Engineering at NTU, Singapore. So I think as a start, for those of you who may not familiar with Nanyang Technological University in Singapore, I'd like to give a brief introduction. So NTU Singapore, we are located at the west side of Singapore Island with a faculty strength about 1,700, and we have around 2,000 research staff, including postdoctoral research fellows, research associate, which has master degree, and we have around 30,000 undergraduate students, and then including another 3,500 PhD students. Well, NTU was starting as an engineering-focused university, but later expand to have more disciplinary, including business, science, humanity, even arts, social science, and education. And very recently, we include a new medicine school in the university. So here is our campus. I have to say the campus is very large and also have many greens in Singapore. And NTU is not only about fundamental research, since we have a large engineering school, and therefore test bedding for technologies is another important aspect that NTU very much like to promote. So I just list a few that's relevant to civil engineering. Shown here, this is a student hall, and this is the one of the very first that we are using so-called the prefabricated volumetric construction. Basically, the entire unit was fabricated offsite and then delivered on site for very fast installation. So this is one of the student hall that using and test bedding this PPVC technology. Another very interesting development on campus is this stadium by using the mass engineering timber. Well, even though MET has been used in most of the other continental countries, but in Southeast Asia, especially in Singapore, using MET is actually not popular. But due to the recent call on sustainability, so the MET has been tried and building this big auditorium on campus using mass engineering timber. Another interesting is we have an on-site experimental waste to energy research facility by experimentally study the gasification technology for the waste incineration and convert also to energy. And this is also on our campus. Another relevant about transportation is we have the very first autonomous full-size bus that are running on campus, running around the campus. So NTU is really a live test bedding for various technologies. And about my research group, I've been with NTU since 2010, and our focus is mainly on construction materials. In particular, we work on high-performance construction materials, such as engineered cementitious composites, or another term called bendable concrete. We also have strong interest about intelligent construction materials, such as self-healing and self-sensing. And in Singapore, in the local context, because of the very limited natural resource, so waste to resource for construction materials is also another important area which my group have interest and study on. I think in general, if I want to put our approach, we very much focus on the fundamental mechanism study. And for the purpose, we like to develop and understand the materials and to formulate and develop new materials. But we are not just satisfying and stopping here by publishing journal papers and IPs. We actually was hoping that we can bring our materials to the real world applications. So locally, we have different trials that the material been developed in the lab. And today, the focus or my presentation will be mainly on this waste resource for construction materials. So let me give you some background. Well, Singapore is a small island. The solid waste management basically follow this flow chart. You will see about 60% of the daily waste generated, which is about 20,000 tons per day, will be recycled. And then the remaining 40%, the majority, about 37%, is considered as the incinerable waste, will be sending to the incineration plant. After incineration, well, certain amount of energy is recovered. Very small amount of metal was recovered as well. The remaining ashes, including the bottom ash, as well as the fly ash, will be sent to a landfill. And as of now, there's only one landfill available in Singapore. Well, that is an offshore landfill called Semakau. It is actually being connected by several small islands. So this Semakau landfill has been developed and commenced since 1999, and it costs more than 600 million of Singapore dollars. And the expected lifespan is only have another 15 years. Right? In the very beginning, the expected lifespan will be up to 2050. But because of the growth of population and the waste generation increase annually, and therefore the lifespan now, expected lifespan is shortened to 2035. And therefore, this is really a pressing issue locally in Singapore. And that's why the solid waste management becomes very important in the local context. And our research group mainly working on this incineration bottom ash for a good reason. I think we all know that IBA is much less hazardous than the incineration fly ash IFA. And because of that, it representing a higher potential for the reutilization as a civil engineering materials. Other than that, we also understand IBA has a much larger quantity. Typically, it will be more than 70 to 80% of the total ash generated. That is actually IBA. IFA representing a smaller portion. So in Singapore, the daily production or generation of IBA is more than 1,500 tons per day, which representing more than 50 or say 60, 70% of the total waste that being disposed of at the Semakau landfill. And therefore, if we are able to deviating IBA from landfills, we think that that will create a significant impact and solution to the waste management plan and strategy locally in Singapore. But if you look at from the literature, the IBA is mainly used as aggregates, and most of the time we will say it is used as a secondary aggregates because of the lower strength grade compared to the natural aggregates. So showing here, even locally, this has been tried to use IBA as the road-based aggregates. In 2002, in a stretch of the road in the west part of Singapore, the base course was built by using IBA as aggregates. However, at that time, the major concern will be the heavy metal leaching. As we know that Singapore as a small island, the entire island being used as a water catchment. And therefore, the water quality is really a serious concern here. So the tolerance for heavy metal that leach out from the IBA aggregates is very stringent. And therefore, certain pretreatment is necessary. Unlike, I know some other countries, we are treating IBA as a non-hazardous material, and we can use directly after simple treatment. So here, the treatment cost is about $30 per ton. Another proposed use of IBA is as concrete aggregate. However, it has been observed in the experiment in the lab. Actually, when IBA is used as concrete aggregates, often it will react with the surrounding cement and generate hydrogen gases, which will cause cracking. And one way to overcome that is to use high temperature vitrification. So to convert IBA into glassy material that is stabilized. However, this treatment is associated with high temperature and high energy. That will make the IBA cost increase to $100 per ton. And therefore, if you compare to the cost of the natural aggregates in Singapore, I have to say the aggregates in Singapore are most been imported from the neighboring country because Singapore does not have aggregates available. But even considering this transportation, the natural aggregates cost is only about $15 per ton. So if we look at those numbers, we will pretty much say to use IBA as aggregates is not economically attractive at all. So recognizing this research gap, we formulate our research direction and statement. Basically, locally, we like to deviate IBA from the landfill, and therefore we are able to prolong the lifespan of Semakau, which is the only landfill in Singapore. Other than that, we're hoping to create local resources from the waste. Here, in this case, is IBA, because Singapore with very limited natural resources. And the main gap is we know that IBA was mainly used as aggregates, which is not economically attractive. So our approach is we like to strategically use IBA for high value either ingredients or even we can produce as the products. So I think here the keywords is we should focus on function and special attributes. So let me give you one example. So showing here is aerated concrete. Well, compared to the typical concrete, aerated concrete, the unit price is much higher. Well, we'll say it's about 2 times compared to the typical concrete. And it's because it's prefabricated most of the time and it's lightweight, right? And therefore, that representing a special and unique function or say special attributes of a product. So when we actually formulate our, our research scope, we actually follow that direction. So our methodology, I think very important is we consider, we actually first recognizing IBA is a highly heterogeneous material. And therefore, if you want to achieve so-called this strategic application, one very important part will be you need to know what you have in the IBA. And therefore, the sorting becomes a very critical portion that enables, we call the strategic utilization. After the sorting, we need to know the characterization of the resulting sorted IBA. And only when we know the IBA we have, the input material, we can start to thinking of what kind of potential application in the category of civil engineering materials that we can do. So we know that IBA can be used as aggregates, and certain portion of the IBA may be able to consider as a silica source for supplementary cementitious material or even alkaline activated material. And for another portion where the calcium is rich, we can consider to use this as a lime. Well, and then later we found out actually IBA have certain aerating potential, and it would retard the cement hydration. And it can also be used as a sorbent or other very interesting material for high strength and lightweight, such as aerated concrete. A certain characterization has been used to discover the underlying mechanism and try to characterize the material performance. And then we go through this iteration, and then you will know that what kind of sorting is necessary in order to optimize the material's performance. So a very quick summary about the several steps that we're going through the entire study. So after we collect the mixed IBA, the average IBA, because we recognizing actually the IBA property changes with time, with different season and different location actually. So after we will first try to do sieving in order to have different size fraction. And then we'll use a magnetic, try to do the separation for the ferrous and the non-ferrous material. And with the non-ferrous material, it contains a certain metal, but also contains a certain non-metallic material such as glass. Then we will use the density separation method, try to separate the different type of non-ferrous materials. So for the different category, as we can see here, the ferrous, the non-ferrous, this is metal, and this is non-ferrous, about glass. We'll go through chemical composition, try to do further characterization. So I just want to maybe say highlight a few interesting observations here. So for example, we found actually the calcium-based material was mainly concentrated at smaller particles. That could be ferrous and that could be non-ferrous. Whereas the silica-based material was mainly concentrated on the glass portion. Whereas the iron-based material was mainly focused on the ferrous portion, but that's mainly on the large particles. Another interesting observation, because of the reporting of gas generation, as shown before. So actually, we also identify the hydrogen generation from IBA at different size proportion and different type of IBA is not the same. And that's mainly due to the presence of metallic aluminum that when it interact with alkaline solution, it will generate hydrogen gas. So the factors influence this gas generation depending on the type in the IBA fraction, being the non-ferrous, being the ferrous, or being the glass. And the size fraction also plays an important role, the pH in the solution, the temperature of the reaction. So those are the main factors. So when you actually measure the average gas generation, if we mix all the size proportion together, it's about 1%. We would say about 1% of the metallic aluminum content on this average IBA. However, when you actually measure at different type and different size fraction, we find out the large non-ferrous particles contain and will generate much more of the gas. And when we actually observe those particles on the SEM and VSD image, often you will find out a large chunk of metallic aluminum in the non-ferrous IBA in the larger particles. And we believe that's because of the high ductility of the non-ferrous, the metallic aluminum that will basically be present in the non-ferrous part, and especially in the larger particle. Because even going through the incineration process, well, because of the high ductility, the metallic aluminum is not so easy to be break down into the smaller pieces. And with such a high gas generation potential, we'll say it's about 10 times. You can see here is more than 10% of the metallic aluminum in the larger particles. We will see a certain portion of the IBA, it actually can serve as the aerating agent. Because we know that even in aerated concrete, that the factory using metallic aluminum powder as the gas generation or gas forming agent. About the trace element, in general, we are using this digesting method in the hydrofluoric acid. So we found out actually the smaller particles, you will see that in the ferrous, the smaller particles shown in the black shaded area is often contain much more trace element. Well, in the contrary, the glass and the large non-ferrous particles are much cleaner, shows a much less trace element. So that's an indication about the concern of heavy metals. And in a separate study, when we try to study the influence of using IBA in a cement, so here we replace 20% of the Portland cement by using IBA with different size fraction. So it's very clear to see that by using smaller fraction of the IBA, it has a very clear retarding effect. So under SEM, we can observe this is on the pure cement after 1 hour and up to 10 hours, the hydration. So you will see the hydration product formation on the surface of the cement particles. However, when the smaller particle size of IBA is used, well, you find out a very clear delay in terms of the formation of hydration product. And this is pretty much because of the presence of more soluble calcium-bearing substance, as we mentioned, that's mainly in the smaller particles. And therefore, that's prohibit the dissolution of the tricalcium silicate, and therefore delay the hydration. Another potential mechanism is we understand with a high content of trace metal, the heavy metals in the smaller particles, that may actually hinder the nucleation of the Portlandite and the CSH. It's very much like the heavy metal poisoning to the cement. But with this observation, we can say potentially the IBA can be used as a retarder that try to delay or retard the cement hydration. So with the previous characterization, if you look at the different size fraction shown here from less than 300 micron all the way to larger than 6.3 millimeter, and consider different type ranging from glass IBA to ferrous IBA and to the non-ferrous IBA, well, we can say that as a glass portion, about 40%, that is very rich in the silica. And therefore, that potentially can be used as a supplementary cementitious material and alkali activated materials. As for the ferrous, the larger particle, well, that will be ideal because of the mechanical strength that can be used as aggregates. Well, for the large non-ferrous particle, because of the presence of a high content of metallic aluminum, that could be an ideal candidate for the aerating agent. And I would say the smaller particles is more problematic because of the high trace element, the heavy metals. However, with this 35%, we can consider as a rare metal recovery, and it also very rich in the calcium source. So potentially, it could be used as a calcium source replacement. And this also shows the retarding effect, and also the smaller particles with a high surface area that could be considered to use as a sorbents. So with this, I will just quickly demonstrate several potential applications in terms of construction material. So the first trial approach, we are using hydrothermal treatment to treat IBA, because by doing that, we are able to increase the surface area. We are able to stabilize the heavy metal. So showing here, you find out the BET results that after the treatment, the absorption capacity is very much increased. And also because of that, when we see this surface area, the treated IBA is actually much improved compared with the raw IBA. And we also try to study the pollutant absorption capacity. So showing here, because of the increased surface area and reduced heavy metal leaching, it actually enhanced the electrostatic forces and the heating energy with the 3Ca and TCS, and therefore it improves the absorption of the organic pollutants. Another initiative is we understand, when IBA be used as SCM, the major concern is the gas generation. And therefore, we use alkali to treat IBAs. And we found out by using different type of alkalis and different concentrations, well, compared to the untreated one, and this is the control without adding any IBA, we found out after the treatment, we can significantly remove the metallic aluminum, and therefore the density could be maintained. And also by doing this treatment, the pozzolanic activity of the resulting IBA is improved compared to the untreated IBA. So the conclusion shows that after the treatment, the IBA can be used as a SCM with more than 70% of the reactivity compared to the unreacted IBA. And because of the removal of the gas generation, the strength of the resulting IBA motor is actually much improved compared to the untreated one. Another interesting idea is we can use the large non-ferrous metals, the metallic aluminum, the large non-ferrous particles as the gas forming agent. So let me first show you to produce the aeratic concrete. So perhaps let me hide this. So this is in the lab. We want to demonstrate the aeration capacity. So this is the paste by adding the IBA. So you can find out very significant aeration capacity once IBA is interact with the cement paste with high alkalinity. Right. And we understand the advantage of this AAC is it's lightweight with excellent thermal and acoustic insulation. So here we're proposing there's a potential combination. We can use the large non-ferrous metal from the IBA as the gas forming agent. There's another potential that we can use the smaller particles as a line replacement to provide the calcium source. As we can see, this is the typical proportion for AACs. Here, well, people using lime, fly ash, and aluminum powder from the raw material, the virgin material. But here we are considering you could actually use a different size fraction and different type of IBA to replace the different ingredients. The IBA glass can be used to replace the fly ash to provide the silica source. And also the autoclaving is a good method to reduce the heavy metal leaching. And it representing the high value products. As we mentioned, is $170 per cubic meter as compared to the normal concrete. So here I just want to highlight in the lab, we try to develop the resulting material compared with the control. So we can basically reduce the density to the range about 700 kilogram per cubic meter. And by using the large non-ferrous particle as the aerating agent, we are able to generate more gas, and then we are able to further reduce the density compared to without doing the size fraction, the sorting. Right? And because of that, you also find out, compare these two lines, the strength versus density ratio is improved by using the non-ferrous IBA as the aerating agent. And there's another attempt that we combine different combination by using line replacement, fly ash replacement, and or the aluminum calcium silica replacement. And we also observe the improved property in terms of the compressive strength ratio to the density ratio. The heavy metal leaching from the resulting IBA AACs clearly show that both the monolithic leaching and also the polarized leaching they are much lower than the standard requirements. So we can say the concentration of heavy metals leach out from the IBAC are far below the limits during either the use phase, which is the monolithic, as well as the after the end of life, which is the pulverized leaching. Another attempt, we try to develop a high-strength binder by using alkaline activation method. So as the first starting point, we try to understand what is the chemical structure after the alkaline activation. So here is a general IBA, and after the alkaline activation, we are using a sequential chemical extraction with the idea of removing the calcium phase by using the salicylic acid methanol SAM method. And then after that, we are able to do using the FTIR, try to specify and understand clear what is the calcium phase being removed. So we identify in this case about 20% weight percent of the material is CSH and the prisonate, which is also a calcium-based minerals. And we can further remove the alkaline silica-based phases by using the HCl. And the NMR will give us the resulting residue here. And then we identify about 70 weight percent of alkaline silicate gel, which is we call a geopolymer gel with a silica to aluminum ratio about 2.52. With that understanding, we start to tailor the high-strength binder by only selecting the glass particles as a precursor. So after doing the analysis and the mix design, we're able to achieve a binder strength of 70 megapascal. However, the NMR analysis showing that this type of alkaline activation of glass basically will give us a binder mainly consists of the sodium silicate gel, about 50%, and then the remaining will be the unreacted glass particles. And we understand the sodium silicate gel, the hydrostability is a concern, meaning after the binder exposed to water, well, the strength will degrade to a certain level. So the hydrostability will still need to be further improved for this type of high-strength binder. And then by understanding that, we try to consider if we are able to mix using IBA glass to form a binder, and then using the large non-ferrous particle as an aerating agent to produce we call a high strength and the low density AA-IBA binders. So mechanically, we can clearly show that the resulting aerated concrete by using glass as the matrix and the large non-ferrous particle as an aerating agent clearly shows a much improved compressive strength versus density ratio, the black curve here. And not only that, because of the combination and addition of this non-ferrous part with the glass, resulting the formation of the CaSH and CSH on top of the aluminum silica gel, and also we call the that unstable sodium hydroxide gel, sodium silicate gel, sorry. And therefore, you find out after the addition, the mix of the non-ferrous particles and the glass, the hydrostability actually was improved. So with the increment of the non-ferrous IBA, so on one hand, this IBA was serving as the aerating agent, but on the other hand, it was also provided sources to form CaSH and aluminum silica gel. And the leaching behavior shows the majority of the trace element is satisfactory. However, the copper, the chromium leaching will be a potential concern because it shows a higher leaching of the copper and the chromium. So in conclusion, based on our findings, we found that IBA is highly heterogeneous, and therefore sorting is actually the critical part which enables the strategic application of IBA. And we also find out the heavy metals are most concentrated in the smaller particles. the glass IBA is around 40%. The IBA particles we have can be used to provide as a silica-rich sources. The large non-ferrous IBA, which is about 15%, is a good potential for irradiation. Whereas the 35% of the smaller IBA particles can be considered as a retarder, as a calcium source, and can be used for the rare metal recovery. Then the remaining 10% of the medium to large ferrous particles will be a good source for aggregates. And also throughout this presentation, we demonstrate that IBA can also use for the synthesis of sorbents. The high strength cementless binder is purely using glass, and also the lightweight aerated binder with a density less than 700 kg per cubic meter, and with a compressive strength more than 5 MPa. And the heavy metal leaching is generally acceptable. So with all this, I will end my presentation. And if there's any questions, I will happy to answer in the time that we have this Q&A session. Thank you.